What is happening, everyone? This is another collaboration video. And again, with Algebra at Algebra 1. Go to his channel. A link in the description. Put a card up. Do all those things. He does a video a day and has been doing so. I don't know where he's at now. 260 days, 265 days. Might be longer. So it's interesting. It's a lot of work. And he's pretty eclectic as far as the problems he's picking. It's very interesting the way he solves stuff. So check him out. That's awesome. You should really support him. And he posed this problem. And the way this usually works is we both look at the problem, we solve it, record it, we edit together and post it. We don't really collaborate as far as how we're going to solve these problems. Maybe in the future we'll do that. Well, that's not true. I think in one we tried a little bit, split it in half. But so I don't know how he's solving this. He doesn't know how I'm solving this. So if you're watching this, you might get two completely different solutions. You might get the exact same solution. And I mean method, not necessarily the answer. I'm sure we'll both get the same answer, but maybe different ways to get there. So these are fun videos, interesting. Again, subscribe to Algebra, please. Support him and his channel. So the question here is, we have 8 boxes. Each box contains 6 balls. Each ball is of n colors, such that no 2 balls in each box are the same. So the colors in each box are unique. And then no 2 colors occur in more than one box. And we want to know what's the smallest possible n, or smallest number of colors, what this would be possible. So I did this by a grid. And the grid kind of reminded me a little bit of a Cayley table. So I thought, why don't I try that? And so I developed a sort of pattern and algorithm to this. I think I haven't really spent too much time thinking about a generalization, but I had thought before I started this video of a way to look at this a little differently. I'll talk about that at the end, but I don't have too much worked out in that realm. I'm going to need more room. Let me write these closer together. So each of these will consider maybe a set. These B's here are box 1, box 2, box 3, box 4, box 5, box 6, box 7, box 8. So each of these boxes has 6 balls, or in our case, just going to be 6 elements. And each element is going to be unique color. And we have to make sure that we don't place, if I have 2 colors in B1, those 2 colors can occur also in B2. And the way I thought about doing this was just to start listing colors. And I'm going to do so just symbolically. I'm not going to literally write colors. So box 1 will be 1, 2, 3, 4, 5, and 6. So box 1 has the first color, second, all the way up to 6 colors. That means that no other box can now have more than 1 number. So I'm going to place 1 number in each box and stop. So I can't put any other number in box 2, 3, 4, 5, or 6, or 7, because if I did, then there would be 2 boxes with the same color. So now I have to come up with new colors to put in box 2. And so the way we can do this is say, well, I'm going to put color A, B, C, D, and E. Let's keep track here of how many we have. So we have numbers, we have 6, lowercase letters. We now have 1, 2, 3, 4, 5. All right, so I can repeat this pattern descending here. You can see why this works, because box 2 has 1 and all of the letters. Box 3 has 2 and 1 letter. 3 has, right? So far, none of them repeat. And I can continue this pattern for a while. So uppercase letters, we're going to have A, B, C, D. So these are uppercase. There's 4 of them. And I can repeat this pattern. So if we look at box 1, 2, and 3, no two colors occur in each. They're each unique, so there's no repeated colors in box 1, 2, or 3. And so if you think about box 4, 5, 6, and 7 at this point, I know 8's blank, but there's a reason for it. If I want to put another number in box 4, I can't because 3 is already in there and all of the numbers are in B1. I can't put a lowercase letter because all of those are in B2, and I can't put an uppercase letter because all of those are in B3. So I cannot repeat any number, lowercase or uppercase letter for 4, 5, 6, or 7. Now I'm going to use Greek letters, alpha, beta, lambda. And we have 3 of those. And I can repeat here. And for the same reason, box 4 has all the Greek letters. So I cannot repeat any more Greek letters in 5, 6, or 7, because if I did so, then they would share. So we're running out of symbols here, but let's do shapes. So a triangle and a square. And there's 2 of those. And I'm going to repeat it like I did the pattern. And so you can see that, again, we're good. We are not repeating any of these boxes, colors. And box 5 has all the shapes, so then we cannot add any more shapes to 6 or 7. And so lastly, well, not lastly, here I'm going to put a smiley face. And I got 1 smiley face. And here I'm going to put algebra. So algebra 1, he's a person, and I got 1. All right, so how many? Now, each box is unique. There's no overlap as far as, well, there's no 2 colors in each box. Right, each box has unique colors. No 2 boxes have the same 2 colors. So this conforms to the pattern we need, but we have 1 box left. So let's look at how many we've used so far. 6, 4, 15, 16, 17, 18, 19, 20, 21. Is that 21? 10, 20, 22? I should have added these. 10, 15, 20, 21, 22. All right, so now we have to see if we can construct from box, for box 8, from the existing letters, because we want to minimize this. And so let's see. We can use, for box 8, we can do algebra and smiley face, because those are in 2 different, but that means that we can't use a shape, because the shapes in box 6 has smiley face, box 7 has algebra, so we can't use a shape now. Can we use a Greek letter? If we use a Greek letter, no. Because if we use alpha, well, can we use a Greek letter? If we use alpha, so right now we have this and this, so we can't use beta and we can't use alpha. So we can pick at this point a Greek letter or a number. Let's pick a number. So now I have 4. So box 8 has algebra, smiley face, and the number 4. I can use a lowercase letter. Yep. So we can't pick C. We can't pick D. We can't pick E. But we can pick B. B works because we haven't used a Greek letter and an uppercase letter. But the choice of B now eliminates, we cannot pick any Greek letter. We cannot pick any shape. We cannot pick any lowercase letter other than B and any number other than 4. So uppercase, lowercase, numbers, shapes, Greek, algebra, and face are all burnt, I think. Right? Yeah. So I think this is correct. So now I want to make sure that we cannot duplicate. So let's see, if I have algebra, smiley face 4 and B, we can't use any lowercase. We cannot use any other numbers. We cannot use shapes. Well, if I switch from 4 to 2, does that help? Let's see. I think it does. Remember, because we're trying to minimize. So I still can't pick any uppercase, but I can pick a Greek letter now, I think, because we can't have shapes. So algebra, smiley face, none of that has B, none of that has 2. Now 2 we can't pick ABC, and B we cannot pick. No, we can't. This is 1, 2, 3, 4. I think that's it. I think that's the only possibilities here that we got. So algebra, smiley face, 2 and B. Just make double sure here. Well, my choice of B is bad, right? Because I can take B off. And if I pick A, now I can pick a Greek letter, can't I? Algebra, smiley face, 2A. And I can't pick beta. I can't pick lambda, but I can pick alpha, right? Because I got 2 algebra. B4 is not doubled. Yeah. But I cannot pick any uppercase letters. So I have a number, lowercase, Greek, smiley face, algebra, no shapes, no uppercase. I think that's it. All right. So that's box 8. So I need one more color, so I'll just invent another color. Let's call it star. So that means B8 is algebra face 2A alpha star. And that means we have to add 1. So that's 23. So that should be minimal. 23 should be the smallest amount. I'm pretty certain. All right, we have a number, we have a letter. We can't use uppercase. We can use Greek because we didn't burn box 4. So yeah, I'm going to say that's good. I'm going to say that 23 is the smallest. Yeah. So I didn't generalize this. This is very specific for this specific problem. But one thing I noticed is this. If we think about in terms of a graph, the boxes and the colors match, right? But none of the boxes would have an edge to another box. So this would be a bipartite graph. Bi meaning 2. And so if we had boxes here, B1, B2, all the way up to B8, then we can have our colors here, C1, C2, C3, and then we can conceivably draw edges. This would be very messy. I'm not going to do this, but I wonder if we can generalize this by using bipartite graphs. I don't know. That might be better as a separate video looking at bipartite graphs in terms of this problem to see if we can generalize this problem for any finite number of boxes and colors. Because one thing you see maybe is that no two colors occur. It can't have a cycle. So let's say I have B1 goes to C1. Now B2 can go to C1, and it has to go to a different color. But yeah, I think you can't have a 4 cycle here. But anyway, for another video, that might be an interesting way to do it. Here's how I did it. I sort of went through a grid, a set, so to speak, and then I constructed my last set. So I think 23 is minimal. The largest would be, if each thing is unique, would be 48, right? So somewhere between 6 and 48 would be the number. And I think 23 is it. I think that's going to be all for this video. Again, I might do this later with some graph theory and look into that a little bit. So we'll see how Algebro solves it. Again, subscribe to him. He's awesome. And that's it. So thanks for watching.
Hi guys, this is Algebro. As you guys know, this is a collab with Dogmatic. I don't think I mentioned this, but Dogmatic is a great YouTuber. When I watch his videos, it teaches me a lot. He's a very informative video maker, and his videos are very complex. So if you guys like my videos, you guys will definitely like his videos. And yeah, off to my solution. Okay guys, let's try to solve this. So this is a 2000, I don't know why I wrote 2009, this is 2001 USAMO, or USA Math Olympiad question 1. So each of 8 boxes contains 6 balls. Each ball is encoded with n colors, so that no two balls in the same box are the same color, and no two colors occur together in one box. So that no more than two colors occur together. No two ball, there's no n is possible. So there are 8 boxes. There's box number 1, box number 2, box number... you probably won't be seeing this. This is just me working through it to get an initial grasp on the problem. Okay. Each of these contains 6 balls. So 1, 2, 3, 4, 5, 6. And then let me just copy this. Can I do that? Yeah. Okay. So this is the problem. Each ball has been colored with one of n colors, so that no two balls in the same box are the same color, and no two colors occur together in more than one box. No two colors occur together. Oh, so we can't have, like, I understand that now. So we can't have, like, red and blue in one box, and a red and blue in another box. We'd have to have a red and blue, then a red and green, or something, I think. Okay, so n, we need to determine the smallest integer n for which this is possible. Okay, so n, clearly, no two balls in the same box are the same color. So, let's just go up. So, if n is 1, that can't work, because then you'll have red here and red here. That wouldn't work. So, n cannot be 1. N cannot be 1. Let's say it's, well, n has to be at least 6. 6 is less than n. I'm going to use red, or blue, I'm not going to use red. Because 6 is less than n, less than or equal to n. because we have to at least have this. We have at least have to have every every ball in each box will be a different color, so we have to at least have that many. So, oh shoot, sorry. Okay. So we at least have to have 6, and at most 48, I think, because that would be a different color for every single ball. Yeah, and is less than or equal to 48. Okay, that's a pretty large range, but at least we've narrowed it down. So, now let's look at this. Let's say we have this colored one. I'm just using numbers instead of colors for now. 6. So each of these are different. And then if we have 1 here, we can't have any of these here because they can't occur together. So we have to have 7, 8, 9, 10, 11. Yeah. So that makes sense. So we can't have. Oh wait, is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Yeah. So we can't have any of these here with 1, because that would be 2 colors occurring together in more than one box. Okay, so now that we did that, why don't we try to put 2 here? 2 can go with any of these. It can go with not any of these. Can't go with 1, 2, 3, 4, 5, 6. But it can go with 7. Can it go with 8? No. So here I think we have to go, because we can't choose any of these because they can't go together with 7. So I think now we're up to 15. Okay. Um, Now we can choose 3, and it can go with any of these. So if we choose 8, and then 8 can go with any of these. So we can choose 12, and then 12 can't go with any of these. 8 can't go with any of these. 3 can't go with any of these. So 12, 16, 17, 18. 18. Okay, continuing on with this pattern, 4 can't go with any of. 4 is a new number. 4 can go with any of these, so we're going to choose 9. 9 can go with any of these, so we're going to choose 13. 13 can go with any of these, we're going to choose 16. 16 can't go, and none of the other ones can go. I'm not sure if we've fully eliminated all of these, so I'm going to just not update that now. 16 can't go with any of these, so we have to choose another one, 19, and then we're going to go 20. So then we can go to 5. 5 can go with any of these, so we're going to go 10. 10 can go with 14, which can go with 17, which can go with 19, and then we're going to go to 21. And then 6, 11, 15, 18, 20, 21. So which numbers haven't occurred together yet? 1 and 3 haven't occurred together. Have they? No, they haven't. Wait, they have. Of course they have. 2 and 11 haven't occurred together. So we're gonna say 2, or we could just do 8, I guess. 8 hasn't occurred with 13. 13 hasn't occurred with 17. 17 hasn't occurred with 20. And can we choose another number? All these have occurred with 2, all with 8, all with 13, all with 17, all with 20. Can't do any of these because these have all already been done except 21. 21's already here. So 22. So n is less than 22. Okay. That gave me a new idea. We could use that diagonal line strategy, I think. So if we redo this, so we have B1, B2, B3, B4, B5, B6, B7, B8, 1, 2, 3, 4, 5, 6. Just copy and paste this. Oh. 1, 2, 3, 4, 5, 6, and 7. Okay, now, so we know it has to start with 1, 2, 3, 4, 5, 6. Do we, no, it has to be greater than 8. If we go this way, 8, do all of these have to be different? No, they don't. No two colors occur together in more than one box. So we have to have pairs of numbers. How many pairs, distinct pairs of numbers can we make? So with 4, 1, 2, 3, 4, we can do 1, 1, 2, 3, 4, 5, 5, I think. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 2, 4, 3, 4. So 1, 2, 3, 4, 5. With 5 we can do, what are we doing here? We're doing, this is 3, this is 2, this is 1. So I think it's just n minus 1, the sum of numbers up to n minus 1. So n minus 1 times n over 2 is, okay, so we need that to equal 8. So for 4, that's 3 times 4 over 2, which is 6. Yeah. For 5, that would be 5. That would be 4 times 5 over 2, which is 10. So that gives us one pair for each of these boxes plus an extra 2 pairs. Maybe that has to equal 48? Let's check. So let's do 7 is 6 times 7 over 2, which is 3 times 7, which is 21. No, I think 10 might be it. 10 is 9 times 10 over 2, which is 45. No, it's 11. 11 question mark? So let's think about this. We need pairs of numbers. We need how many distinct pairs of numbers? Why don't we go through this again? So out of all of these, we have 6, and then of course, if we just choose an arbitrary one, we can't have any of these, so we can choose none of these. So 7, 8, 9, 10, 11. So we have, I'm sure, n is less than or equal to 11, which is less than or equal to 21. Okay. Now, let's continue. Can we make, let's choose, 1 has appeared with all of these, so it's a bad option. If we choose 2, that has appeared only with these. So we can't do any of these, but we can do any of these. So we can only do one of them. I think what I had done before was correct. And then we have to choose new ones because everyone else has been chosen. So we just have to go to 12. And now let's choose another one. Let's choose one from here, we can only choose the ones. We can only choose one from each of the boxes we've already done. So with this, we need 6 numbers. The top one, we need 6 numbers. This one, since we can choose 1, we'll need 5 numbers. This one, since we can choose 2, we need 4 numbers. 3 numbers, 2 numbers, 1 new number, and then because all the numbers have to be unique, right? No 2 balls in the same box are the same color. Yeah. So we have to have at least 11, 15, 18, 20, 21. And then these last two, do we only need one more? So then, let's find, here we need 6 more, we could choose 1 here, we need 5 more, we can choose 2 here, we need 4 more, we can choose 3 here, we need 3 more, we can choose 4 here, we need 2 more, 1 more. Okay, now, from here, I'm just going to continue this pattern, just to have a cleaner version. 2, and then we choose, 8, 12, 16, 17, 18, and then 4, 9, 13, 16, 19, 20, and then we have 5, 10, 14, 17, 19, and then 21. So here we had another, and then this one's 0 because we could just do the last column, and that gives us another full straight. So for the 7 boxes, we need 21. This last box, what can we do? What did I do here? So let's, oh, and then we can get a full diagonal. So 1 never appeared with, oh, we have to start here. What? 1 did appear with 7. What am I talking about? 1 appeared with 7. 2 appeared with 7. 2 did never appear with 8, which never appeared with 13. 13 never appeared with 17. Am I sure about that? Yes. 17 never appeared with 20. Am I sure about that? Yes. It's 15, so I'm fine. 20 never appeared with 20 did appear with 21. 20 appeared with all of these, so all of these are out. 2 appeared with all of these, so all of these are out. 8 appeared with all of these, so all of these are out. 13 appeared with all... Yeah, so we can't do 13, because 13 appeared with 2. Which one? 2 has appeared with 3 in 3 columns, so all of these first numbers have appeared in 2 columns. All of these have appeared in 2 columns. Or in 2 rows. So, if we just choose an arbitrary one, because all of them have showed up at the same number of times. This crosses out all these, this crosses out all these. So then, choose 2 is crossed out, 3, 4, 5, 6 is crossed out, and then 7, 8, 9, 10, 11 is crossed out. So then we could choose any one of these. We'll choose 12. 12 crosses out all of these all of these rows. And does it appear anywhere else? No. 13. Oh, we have to cross out all the ones that those appear with. So 13, 16, 14, 15, 17, 18. Then we're left with 19. And that crosses out these two, which crosses out these two. I'm not sure about that. Because that would mean that I made a mistake here. Has 17 appeared with any of these? No. Has 20 appeared with any of these? No. Has 2 appeared? 2's appeared with 13, that's my issue. So 22 is not the answer. So we have 19. And now we need new numbers. So 20, no, we have 20 and 21. We need 22, 23, and 24. Which is convenient because that's exactly half of 48. So we're going to cross this out because I made a mistake here. And we're going to say 24. So I believe 24 is our answer because we know we at least need 21. And then once we've used the 3 numbers that we can from here that haven't appeared together, we need to create 3 more. So 21 I think is our answer. let me just think about that, how to write that a little bit more formally. I believe I'm gonna post, I'm gonna add this to the video because I solved this one pretty quickly. I don't think it's been that long. How long has it been? Yeah, that's a reasonable time. Okay, so if we look here, I explained this before, but we're gonna need 6 different numbers because every number can only appear once in each box. No two no two balls in the same box are the same color. So we choose six numbers here, and then we have to choose 5 new numbers here because we choose an arbitrary one here. And since there are no pairs that occur together in more than one box, yeah. Um, none of these can occur. We do the same thing. We can choose 2 numbers here, and then once we get here, we don't have to choose any, and we get a free row. And then this one, this last one, we can choose 3 numbers by eliminating all the other numbers, choosing arbitrary numbers, and then we have to choose 3 more. So our answer is 24. Let me see if that's correct, because I think there's a very possible chance I'm wrong, although I do see the symmetry with the fact that 24 divides 48 in 2. So we're just going to check the answer. Oh, it's 23. It's 23. I'm not even sure what I did wrong. Did I add these up correctly? 15, 18, 20, 21. Yeah, I'm not sure what I did wrong, but it is not. I hope, since this is a collab with Dogmathic, I hope he got the correct solution, because then that would make one of us 50%. But we'll have to see. I will probably put his video first, so you guys will already know. But I thank you guys for watching. I'll see you guys tomorrow. Goodbye.